too many things. All right. So, number one is really kind of how we ended yesterday. And I know we did not get to practice a ton of them. We're going to do a couple of them today before we get into what we need to get into. But there's number one, you may be able to figure this out too. So, let's talk it through. We've got that the cafeteria allows you to get 1 fruit, 1 entree, and 1 drink at each meal for like a meal unit. If they have 3 different fruits, 6 entree options, and 5 drink options, how many different meals could one make? What do we think? Any ideas on this one? Multiply the numbers together. Yeah. So, oops, sorry, that's going to zoom in. I'll fix that. I have to zoom it in to write somewhat decently, but you guys don't need to follow my brain. So if we have 3 fruit options and 6 entrees and 5 drinks, I just tended to write it like this. We can keep track. How many different meals can we make? 90. Because we're going to take our 3 times our 6 times our 5. All we got to do is multiply them together. So we have 90 different meals. 90 different combinations. I should write meals just so we're clear. 90 different meals. So that's all we need to do with those ones. We're just multiplying how many there are. And again, I said we will practice that a couple more times because we didn't really get through much practice on it yesterday. We kind of just talked it through. So the fact that we figured that out, super happy with, super proud of. Okay, I mentioned it yesterday in the bell work, but here's another one of that same expression where we're going to be doing some substitution into this expression here. Again, I will always substitute in using parentheses. So when my b is -3, I'm going to put it as -3 like this, then being squared, minus 4 times my a, which is 5, times my c, which is 9. And again, we're into our simplifying stuff. We're doing our PEMDAS. Is there anything in my parentheses I can simplify? Nothing within the parentheses I can simplify. Because everything inside of parentheses is just a number. So then we're going to go to exponents. What is -3 squared? 9. The reason I put it in parentheses like this is because it's really important if you were to put that little phrase into a calculator. Yes, dear. Yeah, you're here. If you put it into a calculator without the parentheses, the calculator will tell you it's -9. Because the calculators aren't sure if you meant -3 squared or -3 squared. So you got to make sure you're clear on it. So this should be a +9. And then we're going to subtract. We can do our multiplication here. 4 times 5 times 9. What do we get when we do 4 times 5 times 9? So what do we get when we take 9 minus 180? What's our final answer here? -171. This last one is it's a challenge problem. It's an SAT practice problem. This comes from the bank of SAT questions based on this kind of stuff. So this one is a little bit harder, and it's a little different than things we've done before, but it's the kind of question that'll sometimes show up on SAT. So we've got a bag that has 60 marbles. Here. And a marble is chosen at random from the bag. The probability that the blue marble is chosen is 35. So we want to know how many blue marbles are in the bag. So what we know is our number of equally likely outcomes, and we know our simplified ratio. We put it as a decimal. So I'm going to set this up as kind of an equation, which we haven't really done before. So we have our favorable outcomes is what we normally do on top. So this would be the number of blue. I don't know how many there are, but that's what we want to have here, number blue. Out of our 60 equally likely marbles. So I want to know what goes on the top that makes this equal 0.35. I want to know what's on the top that makes this equal 0.35. And you could just like type things in the calculator like lightning and guess and check. That is an okay strategy. Yes, my dear. What do you mean? More specific. Which is? By what? Yeah. Yeah, we can take, exactly. I'm going to word it a slightly different way, but yes. Okay, so we can either logic our way through it and say, oh, if I multiply those together, it's going to give me some other information. We can set it up like this and go, I see a fraction, and I hate fractions. Whenever we see a fraction and we want to get rid of them, multiply by what's on the bottom. Every time it should get, hello, Sora geese. It'll get rid of our denominator, and that'll leave us with what we want to have. So either way, I want to multiply the 60 and the 0.35 together. Because if I do that, that's going to leave me with just my blank on this side, and it's going to tell me, if I multiply this side by 60, which we'll go through the fraction stuff again another time. If I multiply both sides by 60, my left side turns into just my blank space where it's going to tell me how many blues I have. And if I take my 0.35 times 60, how many blue marbles should be in this bag? 21. So it's taking that favorable outcomes over equally likely outcomes thing and kind of playing scramble the cards. But that came from the SAT College Board practice question bank. So we love a practice SAT question that we can figure out. Questions on any of these? Okie dokie. So we are going to go into your notes packet. And we're going to look at page 5. We're going to do 2 and 3, and then we're going to get into what we need to do today. Because we didn't quite get to the practice problems yesterday. So we're going to start on page 5 doing numbers 2 and 3. And this is just like that first bell work problem. Just like that first bell work problem, where we're taking that fundamental counting principle, where I'm figuring out how many options we have. So, it says when you get ready to get dressed for school, you look in your closet and you find the following choices are clean. You got a red or blue or white shirt, you got jeans or sweatpants, and you got tennis shoes or sandals. So how many different outfits could we make with these choices? So we have, that was exactly what my question was going to be. How many shirts we've got? We've got 3. How many pants do we have? 2. And how many shoes do we have? Tennis shoes or sandals? 2. So what do we do with those numbers? Multiply them. So how many different outfits do we have?
12.
Should be 12. Outfit. Okay? So these don't take a ton of time once we can get our brain wrapped around them. Sometimes it takes us a minute to wrap our brains around the concept. but the calculations on them are pretty fast. So we take the how many we have of each category and multiply them together. Just giving you a second, so still see some people right now. I want to make sure I don't go too fast on that. Okay. Same kind of vibe. We're going to go to the cafeteria for lunch. Give me a sense an easy way to pick this out is the lunch or floats. Those are kind of the ways we toss out these problems. 4 entrees, 5 sides, 5 drinks, and 4 desserts. If you have one thing from each category, how many different lunches could we make? How'd you get that? Multiply all of them. So we're going to multiply our 4 entrees times our 5 sides times our 5 drinks times our 4 desserts. That'll give us our different number of options. And this is, even we can see here with just this few number, why I don't want to draw them out each time and count up my little dots like I did yesterday, because I don't want to have to draw 400 dots. Oh, super gross. So being able to do this with the calculations instead of having to draw it out is going to make your life a little bit easier. Okay? So not super hard, but I didn't feel like sprinting us through it in the last 3 minutes yesterday. Questions on our fundamental counting principle. And we are going to go on to the next page where it says permutation versus combination, and then proceeded to talk about something else entirely to start. So this is page 6. Right under the big title, it says permutation versus combination is the word factorial. And you may have seen factorial before. You might not, but you may have. Tends to be one of those things middle school teachers do to like, it's cool math, it's fun, there's weird things. So I'm going to give us the definition for factorial. And what it is, it's the multiplication of a number there's an M in the word number, and I gotta put that in there. There we go. Otherwise it was just a number. Number by every smaller whole number. Not 0. I'll show you what I mean in a second. So we're going to take these numbers and we're going to multiply them by every smaller whole number. Down to 1. So we read these as 5 factorial, 9 factorial, 13 factorial. That kind of vibe. So what it means for us to do 5 factorial is to take 5 and multiply it by all the smaller numbers. So we're going to take 5 times 4 times 3 times 2 times 1. That is 5 factorial. And we can calculate that just by typing it in the dang calculator. 5 times 4 times 3 times 2 times 1. Should be 120. We are going to be using these in formulas. It's the same kind of vibe with the 9 factorial. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. They're going to get real big real quick. Yeah, it's a big one. So shout it out louder. 8, 0. So 362,880. There is a button for factorial on most calculators. I'll grab my digital version of the yellow calculator to show you where it is on the yellow calculator, because it is kind of hidden. Screen, calculator, oh, I think it's opening on the right screen. Not bad. So we'll do a 13 factorial, which is the same thing. 13 times 12 times 11 times 10 times 9 times 8, on and on and on. Definitely just flicked the tip out of my stylus. Get it. All right. So this is the yellow calculator that I have in the back that you're welcome to use. All the buttons are in the same place. It looks just like this, except it's prettier over there because it's all like square and gray. Cute. And we can type in our 13. To get to the exclamation point, which is our factorial, we have to go into this PRV button. That is because we are in the probability and statistics chapter, so we're going to go PRV. If you look down here at number 3, that is our exclamation point, and it'll do 13 factorial for us. Beastie beast. Beastie beast. So this is, when in doubt, start with the commas. We've got 6,227,020,800. So these factorials get really, really big, really, really fast. But what it means is for us to just take these and multiply them by each other. Sometimes, and a lot of the times in the formulas that we're going to work with here in just a minute, and I was like, and you could just like cut it off and put another factorial. A lot of times we're going to have things that cancel out. We are very rarely going to wind up with gigantor answers. Sometimes, but rarely. 227,020,800. Just because I like to get sure everything's on the same page. Questions on factorials as they stand right now? Okay. Because what we're going to do today, what permutation and combination are ways of figuring out those outcomes, like how many total outcomes, equally likely outcomes. Sometimes it's like when we're looking for favorable outcomes, when things are in different orders. Like there's wonky things, but it's ways of making small groups, basically. So this starts out by talking about a playlist. This is not in your paragraph. This is just a paragraph I should talk about. When you shuffle the songs on a playlist, like on your phone, and you care about what order it's in. So you like sliding things around, putting it in the right order, because sometimes the algorithm goes a little wonky. And you're like, no. If we care about the order, that means this is a permutation. Order is important. Track 5 has to be before track 7. Otherwise it doesn't make sense. So if order matters, it's a permutation. So in the packet, it says, what is a permutation? And then it has this picture. Above it, I'm going to write our definition for permutation. And it is a way of grouping elements into subsets, so just making into smaller pieces, where order, and I'm going to make that bolder, matters. Got a little dramatic, and I can't fit my S. What? Me dramatic? Never. Oh my gosh. Shock. And our notation is based off of this picture here. It's a big P, and it's going to have a little number in the front and a little number behind. Sometimes softwares get wonky with it, but for the most part, it'll be a little number in front, little number behind. And what we call these numbers that are in our notation here is we call this one in front N. And this is the total number of objects or people or things to pick from so like our equally likely outcomes, our total number of options. And then we put something called R, which is the number of things we're picking, the number of things I want. I'm not going to pull all 30 names out of the hat. I'm just picking 3. That kind of vibe. So R is the number of things we choose. And the formula for how we calculate this number involves factorials, which is why we talked about those a second ago. Because the formula we use is going to be n factorial over parentheses n minus r as a quantity, so in parentheses, that factorial. So there's 2 factorials here. So if order is important, we use a permutation. And this is our formula for that. N factorial over n minus r factorial. And some calculators have buttons for these, some calculators do not. As far as I can tell, the SAT calculator does not. So that's why we're going to go with the formula for the most part. If you are confident in your SAT skills, you can use the buttons, but each calculator is slightly different in how they do it. So we're going to use the formula just because it's more consistent, and then we will have access to that because our brain did it when it comes to SATs. So we're going to look through these examples down at the bottom. Make sure you get that formula, and make sure you get down that order matters for permutation. Order is important for permutation. So our first one here is that we've got Rami is selecting 12 family photographs that's going to play in a slideshow. The slideshow doesn't repeat until all 12 go through, so no repeats. 3 photos are of the entire family, 2 photos are of his brother, 3 photos are him, 4 photos are his sister. We want to know how many different combinations there are where his sister's going to be in front. The book words things weird. We are just going to look for how many combinations. They keep wording it as probabilities. We're just looking for those favorable outcomes. And that's the same on the homework too. If you do it as a probability, that's fine, but I don't like that they put that as the word. I want to cross every single every time there's a probability, they're out. So, since order is important here, because we're looking at the first 4 pictures, order matters, that makes this a permutation. So I'm going to put a big P here in the middle. The number in the front is how many things we have to choose from. How many things do we have to choose from in this situation? 12. There's the 12 pictures. And we are looking for the ones that are of his sister. How many are of his sister? 4. So we are going to choose 4 pictures. So we read this as a permutation of 12, choosing 4. So our n is 12, our r is 4. So I'm going to set up our little formula thing. So we're going to make this with the fraction that has our n, which is 12 factorial, and our denominator, which as a, oh my gosh, my brain just totally forgot the word. In the parentheses, we have 12 minus 4 factorial. My brain has totally, like, 100% deleted the word that was like I was trying to think of, and it's gone. No idea what word I was thinking of. That is going to bug me all dang day. Try to remember what word I intended right there. All right, so what I'm going to do before I start trying to type out 12 factorial, because, ew, I want to simplify the bottom one. So I've got 12 factorial over 12 minus 4. We can do that. That's 8. So now our bottom is 8 factorial. When we do that, if we look at this, and I was to write everything out, this would be, you don't need to write the whole thing out. I'm going to show you what you do. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, blah, 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 times 2 times 1. Well, if we look, if I just like block this, that part is 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So when I have that 8 factorial on the bottom, my 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we're going to start being able to cancel some stuff out. The 8s cancel out, the 7s cancel out, the 6s cancel out, the 5s cancel out, the 4s cancel out, the 3s cancel out, and so on and so forth. So all we're left with is 12 times 11 times 10 times 9 to find our number of options here. So we don't have to do all of 12 factorial over 8 factorial. You can, absolutely fine. And if your calculator has a factorial button, that makes it easy. You'll get the same exact answer. What is 12 times 11 times 10 times 9? What are our number of outcomes here? 11,880. Different orders where the 4 pictures are in the front. There are 11,880 ways for those first 4 pictures to go. So we're not going to do them as probabilities for these. When it's talking about permutation versus combination, we're not going to do them as probabilities. That's doing too much. Which is why I don't usually use the textbook problems for this, because they do too much. They do too much. Like, it's a lot. Okay, questions on this first one? Because I know this is a lot of weird. All in one. Yes, my dear. Say that again? We took what was left after we canceled out the ones that were over here. So I canceled out the 8, 7, 6, blah, blah, blah. I have my 12 times 11 times 10 times 9 that's left. And so we multiplied those together. Ask the question. Yes, my dear.
Did we multiply them? From 12 to 1 and 8 to 1, can we divide them?
Absolutely. When we do that, we sometimes may wind up with like gargantuan numbers, so just be careful. But absolutely, totally fine. All right, let's do another one like this. So at the start of each semester, Sari's dorm picks 7 sophomore residents as building aides, 1 for each day of the week. There's 40 sophomore assistants in the dorm. Sari has 2 roommates, and she wants to know how many options there are for the Friday, Saturday, Sunday. Again, we're not doing these as probabilities because that's doing too much. So we want to know how many options there are for Friday, Saturday, Sunday. So we're doing this as a permutation because she wants to know if it's going to be her and her 2 roommates. Because she's saying order's important there. She wants Friday, her roommates want to know. So we're going to do this as a permutation, which we know mostly because I haven't showed you the other one yet. How many options do we have? 40. How many are we choosing?
7.
Friday. 3. Yeah. I get why we see 7. Sometimes, and especially, it happens a lot this year, and it happens a lot on SAT, there will be random numbers in the paragraphs that are irrelevant to what we're doing. So just because you see it as a number doesn't mean you have to use it. So the 7 sophomore resident assistant building aides is irrelevant information.
It's technically just context.
It's context. So there's sometimes numbers in the context that have no impact on the mathing part. So just because it has a number doesn't mean you have to use that number. So we're going to set this up again, just like we did with our little formula, where I'm going to take my n factorial, so my 40 factorial, and we're going to put it over n minus r. 40 minus 3 as a quantity. That was the phrase I was trying to do. 40 minus 3 as a quantity factorial. I knew all I had to do was stop thinking about it and the word would come back. The quantity 40 minus 3. So again, I'm going to simplify that. We'll go with that one. So we've got our 40 factorial. Which part?
Huh?
Which part? I know I can make most calculators do whatever the heck I want. What you got? The factorial?
Yeah.
No. Okay. Go parallel down to probability, and that's in here. Factorial. Right there. Come on. I speak most calculators. All right. So on this one, if you do both of these manually, you're going to wind up with gargantuan numbers to do 40 factorial and 37 factorial. But if we notice with our canceling out like we did on the last one, if I do 40 times 39 times 38, and then we have 37 factorial, because that's all it is it's taking the 37 and continuing that on. That makes it easier for me to cancel these things out. If I take my numerator just to the point where those are going to cancel out, it's going to make my life a whole lot easier. So we're going to get our answer by multiplying 40 times 39 times 38. So how many options do we have here?
59,280.
Okay. I say as long as we see what happened. That does make a difference. Okay. So the other page, the next page, I want to get us through the combination just because tomorrow's when we have class meetings. I want to get us through for sure. Not this one. This one. So we're going to skip the top problem on that last page. We're going to talk through combination, and I'm going to give you the formula for it. And then tomorrow we will practice this and get kind of wrapped up just so that we're not missing much with class meetings. Okay? I don't think I lose any of you guys for class meetings, but I have at least one class where I do lose a good chunk. So tomorrow will be kind of a chill day. We'll finish this up and do like a wrap-up activity for this, and then we'll move on. So combination is very, very similar, but where permutation, order is super duper important Combination is just about groups. Order does not matter. So combination is a way of grouping elements where order does not matter. I always think of it, permutation is Olympics. Gold, silver, bronze. It matters what place you come in, you get a different color medal. Combination is more everybody gets dum-dum across the finish line. Everybody gets the same ribbon. It's like the, if you ever see the mini marathon that they do out here in Indy, everybody gets the same medal when they cross the finish line. It doesn't matter if you are first, if you are last, you're in the middle, everybody gets the same one. So it doesn't matter what place you come, except for your own ego, you get the same medal anyway. It doesn't matter. Everybody gets the same thing. So combination, it does not matter what order it is. Permutation, it does. Our notation is still the same. We're still going to have our n out in front, which is our total. We're going to have our r in back, which is the number we choose. And we have two different ways that we can do this formula. The one that I'm going to do is going to be the n factorial. So starting out the same way, we're going to have our same quantity on the bottom, our n minus r factorial. And it has one extra piece, another r factorial. So this one has three factorials. The other way you can do it, and if this works for your brain, great. It's just two separate calculations. You do our NPR and divide it by r factorial. So it has the same pieces, and in the same places, it just has one extra bit. So you can either do it on the left, doing the whole thing in one calculation, or you can do it in two pieces where you do your NPR and then divide by r factorial. And we will do practice problems for that tomorrow because we are about 2 minutes from the announcements. And I don't want to take us over time. Tomorrow we will do a combination practice problem, and then we will do the bottom four where we're deciding if it's permutation or combination more in depth. So, I'm going to put that up. I do have up here the definitions again if you didn't get those written down. Please make sure you turn in homework 1 that is due today. Homework 2 is due on Thursday. Tomorrow we will also have time to work on it, so if you want to talk through stuff, we're going to be able to do that. If your bell work page gets turned on Friday, we are going to do a quiz on the 14th, which is next Wednesday.